Today let's talk about AtCoder Beginner Contest 379, problem F. First part is description. We are given there is one row trees. We are given an array H that indicates the height of every trees. There is a definition about thin tree J from I if there are two integers I and J. That means I is larger than 1, less than j, less than n. N is the length of the trees. N is the amount of the trees. So if the tree j can be seen from I, it should meet the requirement p less than j. Actually, there is no equal. That means p is less than g, larger than I. HP should less than hj. If every p can meet the requirement, hp is less than hj. So tree j can be seen from I index. This is the definition about seeing trees. There are q times query. For every query, we are provided L and R. We need to find out how many trees which is in the right of R can be seen from L and R. Actually, if a tree, I mean, if for example, if here is L and here is R, we need to know R minus 1, R minus 2, R minus 3, till n, how many trees among here can be seen from L and R. Actually, if one tree can be seen from L, it definitely can be seen from R. So the problem should be for the position which is right of R, how many trees can be seen from L. This will be the true problem. Next part, let's talk about solution. Actually, if we solve this problem use brute force, the time complexity should be O n multiply Q. This will be very high because n and the limitation about of n and Q should be 2,000,000. So the time complexity will be too high. We need to reduce the time complexity. We can process the answer from back to front because and maintain a set which contain the trees that can be seen from a specific node and move the node from back to front. But there are plenty of queries, so we can sort. So first thing should be sort queries by L. For the Q times query, we can sort them by L from least to last. So the second thing, we can process the answer and maintain a set. Actually, it will be a stack. Maintain a stack which contain the trees we can be seen from a specific point. For example, if the current point will be index current point with CUR, so the stack should be contain all trees from CUR to N. This will be stack. More specifically, the first element of the stack should be N and second should be N minus 1. The third should be N minus 2. But there is a detail about the problem. That means if the height of the N point tree will be this high, the second will be this, and the third will be this. That means this minus 2 minus N minus 2. Okay, that means the N minus 1 cannot be seen from 0 to n-3. Actually, it cannot be seen because the left one is larger than current one, so it definitely cannot be seen by any trees from 0 to n-3. So we will know for the stack, the first one definitely should be H. So the first elements definitely should be Hn. Second elements should be n-1. So if we want to add the current index into the stack, we found stat back. That means stat back should be this element is less than current. If the stat back is current, then current head, the height of the tree, we need to pop out the back. That means we need to delete this element. We need to delete this element until the length of the stack will be 0, or the last element of the stack is larger than current height of the tree. Because if the last one is smaller than current one, it cannot be seen. This is a useless trees for the first several trees, for the remaining trees, because it cannot be seen. So this is how we maintain the stack. This is how we maintain the stack. So so the next step, that means third, we can query if the stack dot back, that means start back, actually should be an index equal L. We can process the answer. We can get amount of trees meet requirement. That means if the stack their back dot index, that means if the current index should be L, or if current index should be L, what we need to do is find out how many trees in stack is larger than R. The index of the trees should be larger than R. So if the if the current index equal L, we can find out how many trees in the stack whose index is larger than R. In order to solve this problem, we also need to store the index of every tree in stack. So the element in stack should not be an integer. It should be a pair. That means it should be a pair. The first should be height. The second should be index. So how to query how many trees in the stack whose index is larger than R? We can use the segment tree algorithm. Which can help us to get how many trees is larger than R in below term complexity O log n. This is how to solve this problem. So for the updating about the segment tree, when we pop out an element or add a new element, we also need to update the segment tree. More specifically, the segment tree should be store how many trees from 0 to x. X is a specific index. So for when we add new element, we can update the segment tree. That means we add elements to the segment tree. For it is the same situation if we want to delete a tree. In addition, we also can query for a specific x how many trees from 0 to x. If we calculate how many all trees, so we can use the stack dot size minus query 0, and that means sum 0 to x. The last should be the amount of trees whose index is larger than x. So this is how to solve this problem. Let's assume the answer. First step should be sort. Sort queries by L. So the second step should be maintain the stack. It will be a pair. First element should be the height. Second should be index. And update it from back to front. Third step, if the current index equal L, so update, so get the answer based on R through segment tree algorithm. This is how to solve this problem. If you have any confusion, welcome to submit a comment, or for more detailed information, you can look at my code below this video. Next part, let's talk about complexity. For the time complexity, for every time we add element or delete element or query, we need O log n all time complexity to update the segment tree. So we need n or q times. So the time complexity should be q plus n multiply log n. So this will be time complexity. For the space complexity, we don't need extra time. The space complexity for the segment tree is also O(n), so the final space complexity is also O(n). This is all about the solution. If you have any confusion, welcome to submit a comment or contact me. Thanks for watching.